Okay. In the last problem we in the last video we finished the lecture part. We finished the lesson part or the understanding of what was going on. I didn't explain the plumbing very well there. In fact, I didn't explain it at all because plumbing still baffles me. I know I trust the Bernoulli principle, the Bernoulli equation. Okay, I trust the differences in the pressures and things like that. Okay, so paperweight. So let's just take a look at this problem. This is a classic. This is an Archimedes principle. This isn't Bernoulli. 54, 61, and 63 are classic Bernoulli type questions, okay? So a paperweight, when weighed in air, has a weight of 21.2 newtons. When completely immersed in water, however, it loses like a third of its weight. Okay, so the buoyant force is pushing it. Find the volume of the paperweight. Piece of cake. We know how to do this. Okay, so let's just take a look at this real quick. Let's just set it up, and then you all can finish it. But so on problem 44, got a paperweight. So here's my little globe. Let's make it a snow globe. Okay, so we got a little Rudolph in here with his red nose because he has a drinking problem. So poor little Rudolph is in his little paperweight here, his little snow globe, and when it's sitting on a scale, reads 21 newtons in air. We put Rudolph underwater. Okay, we put this guy underwater, and so all of a sudden Rudolph, the scale reads, and remember this isn't the point. It reads like 14.8 newtons or whatever it was. It's not important because I'm not going to finish the problem for you. All right, so what's going on here? Well, this water is there's a force that's actually helping. There's a buoyant force here. We've got mg here, and up here we know that this is equal to mg. Okay, we know that this is because it's got mg in air. So these two vectors, I didn't draw them very well there because those two vectors should be the same. We've got this little buoyant force pushing up on this guy, an mg. So, but we know this. We know that the sum of the forces in the y direction are equal to 0. And so that is equal to, just looking at this here. Okay. So we've got the buoyant force plus the normal force, and the normal force is what you're trying to find. Okay. When in these problems, well, but we're actually looking for the volume. Okay, plus normal force minus mg. Piece of cake. We've got everything we need because they told us what the normal force. So we know that the buoyant force is equal to mg minus the normal force, the new normal force. Okay, okay. This is the normal force in water, so I'll put a tick on that, like that. Okay, so we know, but we also know that the buoyant force is equal to rho v g. And the volume displaced will give me the volume. So this v is equal to the volume of the paperweight. Piece of cake. You can do that all day long. Okay? So let's go on to another problem in here. And hopefully it's a Bernoulli, and then we'll have one more little video. Okay, a fuel pump sends gasoline from a car's fuel tank to the engine at a rate of 6.19 times 10 to the negative 2 kilograms per second. Okay, so that's the mass that's going. Whoops. It's my wife. We're talking about things. Okay. All right, so here we go. Sorry about that. The density of the gasoline is 738 kilograms per meter cubed, and the radius of the fuel line is 35.1. Okay. What is the speed at which the gasoline moves through the fuel line? Boy, this looks like they're not giving us the materials that we need, but actually they are. This is the continuity equation. So problem 54, let me write down what I have here. A fuel pump. Okay, so the fill rate is, now believe it or not, they are giving us 6.19 times 10 to the negative 2 kilograms per second. Okay, so that's Q kind of. And the density of the gasoline, rho of gas, is equal to 738 kilograms meters cubed. And the radius of the fuel line is 3.58. Okay, so that's the radius. So R is equal to 3.51 times 10 to the negative 3 meters. Okay, there we go. We've got all we need. This is kind of a fill rate, but not really. Okay, but we know that a kilogram is a mass. Kilogram is equal to rho V, right? Because, all right, so I kind of have, I have my volume, rho V is equal to 6.19 times 10 to the negative 2. Okay, so the volume of the gas is equal to 6.19 times 10 to the negative 2 kilograms per second. Oh, this is kilograms per second. Okay. So the volume per second is equal to 6 divided by the rho of the gas. Sorry, I've never worked this problem before, so you were kind of watching my mind work there. And a lot of times when you just match up the units, you've got it made. Okay? So here's what they're saying. Then we don't need to finish. We've done the hard. This was the tricky part. Okay. So now we know that Q is equal to 6.19 times 10 to the negative 2 over 738 kilograms per meters cubed. Okay, because this is kilograms per second. And so when I divide this out, that kilogram goes with the kilograms cancels, and I wind up with meters cubed. I'm just going to divide that so you can see it. So I wind up with 6.19 second e to the negative 2 divided by 738 equals 8.38 times 10 to the negative 5 meters cubed per second. Okay, so Q is equal to A times V. And A is equal to pi r squared. So we're going to get a pretty good volume here because look, we're going to square this guy. He's going to be 10 to the negative 6. Square this guy is going to be around 10. Is it going to be bigger than 10? So it's going to be 10 to the negative 5. So this answer is going to make sense to me. All right, so that's the way you do that one. All right, I'm going to stop here because I kind of farted around with